Hi guys, welcome back to my channel. Today I'm going to be doing a COMSOL tutorial on process control using a PID controller. And this could be for any proportional integral derivative control, which is used commonly in any manufacturing process. They say it could resemble the environment in a combustion chamber where the concentration at the ignition point is crucial. So this PowerPoint was attached with the tutorial files that are included at the link I will have in the description of this video. So in this video we'll be looking at the example of a concentration control in a process, a PID control process, and it will model a reactor with two inlet gas mixtures controlling the gas composition in one measurement point and regulating the inlet velocity of the low concentration gas to achieve a set value. It uses the transient Navier-Stokes equation, since we're doing a time-dependent study, together with diffusion and convection. And it'll use the PID control algorithm to control the inlet velocity. Geometry and conditions. This is our 2D geometry modeling the cross-section of an internal combustion engine. The walls are insulating, I think that's supposed to be, and no slip. And the species diffusivity is this value. Fluid properties of the atmospheric air and initial conditions. So the velocity is controlled at the top inlet and the left inlet. Here's our PID control algorithm. So this will appear as a second component with global ODEs and DAEs interface. So we have UN, which is the controlled inlet velocity of the physical model, equals the proportional parameter times the concentration minus the reference concentration, C set, plus the integral term, so the integral parameter times the integral of this difference, concentration minus reference concentration dt, from time equals 0 to specified time, which in our study will be 6 seconds, plus the derivative term, so the derivative gain parameter times partial derivative of this difference with respect to time. The measured value is obtained using a point probe at the aforementioned measurement point. So we'll produce the concentration and velocity streamlines. Here's an animation they made that shows the density of the velocity lines, the streamlines, moving from the outside to the center as time progresses, and also with a higher concentration at the top inlet, the lowest concentration at the left inlet, and then an intermediate concentration at the outlet and in the center of the engine where mixing is achieved. And then we also look at varying the PID parameters, so we'll do a parametric sweep. So we're going to be modeling two gas streams with different oxygen concentrations that are mixed in the combustion chamber, and the concentration is measured at the ignition point before complete mixing of the streams is reached. So since we have an increased flow of the gas, will decrease the concentration, the PID coefficients will have a negative sign for this PID controller. We're going to be using laminar flow interface for the fluid flow, and also the transport of diluted species interface. If you care to go through all the detailed equations, the fluid flow boundary conditions, the mass balance boundary conditions, that is available in here. Today I'm just going to jump right into the tutorial, but it does go fairly into detail there. It doesn't really go much into the theory of PID control coefficients, but just super fast overview, P is the largest control, or let me go back to the definition. Proportion is the largest control, integral is the second most important control, and then derivative is the sort of fine-tuning control. So each of these will have a coefficient, and you could think of this as sort of like a thermostat. As it approaches the set point temperature, whatever the control is, if it's a thermocouple or other gauging device for your feedback loop, then it will look at the integral coefficient and finally at the derivative. So all of these three play together to fine-tune a feedback loop to allow control of a process and keep it at desired conditions or optimized conditions without thermal runaway, for example. Okay, so let's jump right into here's the results we're going to create in this tutorial. Into the model wizard. So we're going to do new file, model wizard. We're doing a 2D model, and we're going to go to fluid flow, expand that and choose single phase flow, and then laminar flow, SPF, single phase flow. And then we also want to add the TDS physics, which is under chemical, expand chemical species transport, and then choose the first one here, transport of diluted species, TDS. And then we're going to click study and choose time dependent study because we're interested in the startup conditions or ignition. Alright, and now we're already doing global definitions. In the model builder window under global definitions, click parameters 1. And then we're going to enter these in the table. Sometimes it gives you a text file. It won't take me too long. I'll probably just fast forward through this part. Alright, there we go. All done with entering the parameters. As mentioned in the model definition section, the PID parameters are negative because the set point concentration is lower than at the upper inlet. Okay, so our set point concentration is 0.5 moles per meter cubed, and at the inlet our concentration is 0.2. So because our set point is, at the upper inlet the concentration is 1 mole per meter cubed. So because we're going in the negative direction, our control parameters, the PID parameters, are going to all be negative. So just looking at your units for PID parameters, the proportional parameter has units of meters to the power 4 per second per mole. The integral parameter is the same, but seconds is squared in the denominator, which makes sense. If we take the integral, then, and it's with respect to time, then the seconds will go down a power, or since it's in the denominator, it becomes more negative, so the exponent in the denominator goes up by 1. And then the derivative parameter is the opposite, going from P to the derivative of P. The units will not have any seconds in the dimensions. So it's meter to the power 4 per mole. Okay, so in the geometry toolbar, click Insert Sequence and choose Insert Sequence. So we're going to jump down to geometry. Geometry toolbar. So we're clicking up here, insert sequence, and then we're going to choose the PID control geometry sequence in PH that I downloaded before, and build. So you can see how they built this. If you wanted to build it from base principles, they have all the two-dimensional geometries used: circular arc, polygon, line segment, and then convert to solid. And you end up with this cross section of an internal combustion engine with our inlet here, and guessing this is the outlet. Alright, and next add a probe to sample the concentration and its time derivative at the point x equals 0, y equals negative 0.002. So where would that be? Right about here in the center of the engine. In the definitions toolbar, so we're going to go up to the tab right next to home, click on the probes icon, the cylinder with an arrow in it, and choose domain point probe. And you'll see a red dot appear inside our engine cross section, and we're going to change the y coordinate to negative 0.002. In the model builder window, expand the domain point probe 1 node. So there's another item in this drop down menu, and click point probe expression 1, PPB1. And in the settings window for this node, type C_MP and the variable name. So we're overriding the default variable with one of the variables we put in the global definitions. Click replace expression in the upper right hand corner of the expression section. From the menu, choose component 1, transport of dilute species, species C, and then we're going to choose C concentration and mole per meter cube. And double clicking on that will bring you back to the main page. And now we're going to add a point probe expression 2. In the model builder window, right click domain point probe 1 and choose point probe expression. In the settings window for point probe expression, type CT_MP in the variable name text field, and then locate the expression section, and we're going to type CT in the expression field, and it automatically changes the table and plot unit to moles per meter cubed per second. Proceed to import the PID controller add-in and set up the control algorithm. In the home toolbar, click Windows and choose add-in library. So home, where's the Windows? Windows is on the far right. And from this drop down menu, we're choosing add-in, oh no, that's the wrong thing. Windows, add-in libraries. And then we're going to choose from the COMSOL multiphysics drop down PID controller. I haven't installed this before. You have to expand PID controller and then choose capital PID controller. I already clicked PID controller. If it's not already selected, and click done. And then go to developer tab, click add-ins. Oh, there it is. Okay, so now it's adding the PID controller, so you'll see it appear under global definitions under the root node. So we're going to click this new line, and in the settings window for PID controller, locate the controller parameters section. in the middle of the settings tab. So we're going to enter the following settings. Proportional gain, we're going to input our variable defined in global definitions. Integral gain is k underscore I underscore control, and derivative gain k underscore d underscore, oh, that wasn't an end, k d control, and then I have a typo here. Reference value will be variable c underscore set, and click create at the top here. The control variable is now available as comp2.u underscore n underscore control, deduced unit for controller in meters per second. Alright, so now we've got to add materials for our fluid coming into the engine. For the physics setup, you need to specify density, dynamic viscosity of the fluid. For this purpose, define a material. So we're going under component 1, right-click materials, and choose blank material. In the settings window for material, type fluid in the label, and select domain 1. Locate the material's contents down at the bottom, and we're going to enter density, variable rho, and dynamic viscosity, variable mu. Okay, so we have a value of 1.2 units are already kilograms per meter cubed, and then 3 times 10 to the negative 5 Pascal seconds. Okay, and you're now ready to set up the physics of the model. So we'll do the laminar flow physics boundary conditions first, and then transport of dilute species initial values and boundary conditions. So under laminar flow, we're going to right click laminar flow SPF and choose inlet. So we're adding an inlet condition that appears here with a exclamation point on the icon since we haven't added any values. And in the settings window for inlet, locate the velocity. Oh, we have to choose boundary 1. Velocity section, and in the U0 field, type comp2.u underscore n underscore control. So basically that the expression that we were given when we added the PID controller 1. So if you go back in here, right here, so the control variable is now available as this. So we're just referencing that variable for the velocity field. And it doesn't say to change this, so we're leaving this as normal inflow velocity. And now we're going to set inlet 2. Click boundaries and choose inlet under the physics toolbar. So up at the top, boundaries under physics, and adding inlet. So there's 2 ways to get there basically. You can right click on the physics and click this, or go to the physics toolbar at the top. They just showed 2 different ways of doing it. Now we're going to click on boundary 7 at the top, and in the settings for U0 text field, type v underscore n underscore top, referencing our global definition parameter. Now we're going to add an outlet. So physics boundaries outlet 13, that's our only other opening, and that's all we're doing there. So we're leaving static pressure at 0, the default for P0, and now we're adding a wall boundary condition, no slip condition at the wall. In the physics toolbar, click boundaries, wall, Select boundaries 2, 3, 6, and 8. So 2, 3, and not those, so only the inlets 6 and 8. And the wall condition is no slip. We're changing this to slip. All right, and that's it for laminar flow. So now we're going on to transport of dilute species. So we're going to click on Transport Properties 1, and in the settings, locate the convection section. From the U list, choose Velocity Field. So we're changing from user-defined to Velocity Field SPF as the reference for the velocity field. So it'll look to this physics for the solution that was already derived. And locate the diffusion section and the DC text field type D. Initial values. So we're going to click on initial values under TDS. And in the settings for C, we'll put C00, the variable we already set. Inflow 1, we're going to add physics boundaries. Inflow, select boundary 1 only, so our left-hand inlet. And under concentration in the settings section, we're going to change 0 to C_N_ inlet. Inflow 2, add another inflow. Boundary 7 is our topmost inlet. Okay, and then C for this one is going to be C_N_top. Now we're adding an outlet. Boundaries, outflow. Boundary 13 only. And that's it. Now we're going to create the mesh. So we're going to use a finer mesh according to this tutorial. So we'll go under component 1 and click mesh 1. Now we're going to change the mesh size going to the physics controlled mesh drop down, and element size is going to be finer. So this will apply to both the laminar flow and transport of dilute species contributions. Build all. There you go. You can zoom in to see your element sizes. So it's got like a layer of 2 rectangular elements along the outside of the geometry. And then past that boundary layer, it uses triangular elements. Okay, let's look at the inlet. Okay, so we've got triangles at the... Okay, so what are inlet and outlets? It uses triangles even on the edges, and all other boundaries not specified as inlets and outlets have sort of a boundary layer of 2 rectangular elements and then triangular elements becoming larger as it approaches the middle zoom extents. And now for the study, we're going to use a parametric sweep to solve for 2 different values of the proportional parameter Kp. So to add a sweep, we're going to go to the study toolbar, click parametric sweep in the middle here with this 1, 2, 3 column icon. And in the table, we have to hit add, and then we're going to enter the settings into this table. So from the drop down menu, we'll select K_P_control, the proportional parameter. And then for the values we want to sweep, we'll use -0.1 space. I don't know if it won't accept it if you don't have 0, but I'll enter that. -0.1 and -0.5. All right. So now we're going to set up the time-dependent study. In the Model Builder window, click Step 1, Time Dependent, and in the settings, locate Study Settings. In the output times text field, type range 0 to 1 and increments of 0.05. So we're just increasing our resolution here from increments of 0.1 to increments of 0.05. And then another range from 1.1 to 6 in increments of 0.1 seconds. So basically we're just saying we want more points, we want more steps at the startup in the first second. Okay, and now for solution 1, in the study toolbar, click Show Default Solver. So that's the flag icon here, Show Default Solver. And in the Model Builder window, expand Solution 1 node and click Time Dependent Solver 1. Alright, so under Solver, Study 1, Solver Configurations, Solution 1, expanding that, we have Time Dependent Solver 1. And in the Settings window, click to expand the Time Stepping section. From the Method list, so the first item in that drop-down menu, choose Generalized Alpha. So for our methods to choose from for time stepping, we have BDF, Rungakuda, Generalized Alpha, and Initialization only. So for the tutorial, we're choosing Generalized Alpha method, and then from the steps taken by Solver, we're changing from free to intermediate. And you also have manual and strict. This forces the solver to take at least one step in each of the time intervals you specified. Click to expand the advanced section. Why did we expand? I don't know why we expanded advanced. Okay, in the study toolbar, click Compute. And then for results, the default concentration plot group contains a surface plot that shows the concentration at the end of the simulated time span, as well as a streamlined plot of the velocity. Study the solution at time 0.05 seconds and time equals 2 seconds at the end of our study. First, however, adjust the streamline positioning so that the streamline density reflects the velocity magnitude. So we're going to look at the concentration surface plot once it's done here. Alright, there we go. So we've got our velocity surface plot here. But we want to go to the pressure contour. Here's our concentration surface plot. So you've got red is a high concentration, blue is low concentration, and intermediate over here. So, okay, in the Model Builder window, expand Concentration TDS node and click Streamline 1. In the Settings window for Streamline, click Replace Expression. And then we're going to choose Component 1, Laminar Flow, Velocity and Pressure, and UV Velocity Field. So by double clicking, it populates the X component with U in meters per second and the Y component with V. Locate the Streamline Positioning section. From the positioning list, we're changing from uniform to magnitude controlled with a density of 10 and plot. Okay, so there's our new streamline lines, and now we're going to, in the Model Builder window, click Concentration TDS. In the Settings window for 2D Plot Group, locate the Data section. And from the time list, choose 0.05. So right now, this is at the end of the time period for our range of output times. So we're changing this to 0.05 at the very beginning of this startup period, and plot. All right, so we can see that our streamline and our surface plot gradient changed. Zoom extents. And now we're going to look at time 3 seconds, so halfway. And click plot. All right, looks pretty nearly identical to the end time of t equals 6 seconds. Compare the resulting plots with those in figure 2. So those look just like the ones they had at the beginning background information. Okay, so now we're going to plot the PID controlled inlet velocity, figure 3. In the model builder window under results, click 1D plot group 4. In the settings window for 1D plot group, type inlet velocity. Okay, I don't know what I did wrong before, but I'm not sure how much of this I got, but here's the results really quickly. We've got the inlet velocity plot here, KP at the KP control on the blue line equals -1, -0.1, and for the green line, the KP control equals -0.5. And then for concentration, we have the blue line is -0.1 once again for KP control, and then the green line is the proportion parameter -0.5. So that was our parametric sweep with the values we listed, and it did both of those values. So we can see that the green line is more in control. The blue line is overshooting and then overcorrecting and then overshooting and then overcorrecting a few times before it levels off, at least from what we can see in the 6 seconds that we've defined to study. So that means the KP control, or the proportion parameter, is better set to -0.5 than to -0.1. All right, and there's more on this in the attached PowerPoint, which is in the downloadable files at the link. And just like we went over the first case results and stable control, second case is less stable. And so you're better off having a higher, well, and they did a nice animation here as well. So I guess we can do that too. Oh, and then another critical point here, the measured value and the control algorithm is obtained using the point probe. So we had defined that at x equals 0, y equals -0.02, and that's where it's measuring the PID control value. Okay, so if you enjoyed this video and you want to see more COMSOL tutorials, please like, comment, share, and subscribe, and I'll see you in the next video.